given f of x equals 2x plus 1 to the power of 5 times x cubed minus x plus 1 to the power of 4. Sketch f of x. Use Desmos to help you visualize the graph before sketching. So we're going to start by moving over to Desmos, like that. I have already entered the function right here. So I'm going to just enable it so we can see how it looks. Right there. And so when you're sketching this function, what you want to pay attention to are the landmark points. So we have a y-intercept at y equals 1. We have a turning point, a minimum, close to x equals -1 and y equals -1. So it's not exactly at those coordinates, but for sketching purposes, it's good enough. And then between x equals 0 and x equals 1, there is a horizontal part here where we have an x-intercept with a curve appears to be on the x-axis. And again, between -1, x equals -1, and x equals 1.5, -1.5, and then it goes down towards -infinity. And on the right-hand side, it goes up to +infinity. So these are the characteristics you want to identify to help you sketch the function. It's just a sketch, but qualitatively it needs to be accurate. So here I will not sketch the function. I will take a screenshot of it, which you can also do if you're sitting on a computer. Something like that. And then I'm going to go back to my question here. And just to make sure we have enough space, I'm going to remove that. Paste in the graph. Resize it. We are going to annotate it, so you want to keep it fairly large. Something like that. So there's a graph of the function. Now in question B, they want us to predict f prime of x, so derivative of the function, by superimposing a sketch of it onto the sketch of f of x. So if we go back to our graph here, what we're going to do here is we're going to divide the domain into regions that are going to be defined in terms of the slope that this function has. So we are going to start from the left. So we have a x-intercept here. So we're going to have one region here where to the left of this x-intercept our slope is positive. So m is larger than 0. In between the blue lines here, the slope equals to 0. And then as we move on here to the right, between this point and this point at the vertex, at the minimum here, our slope is negative. At the vertex, our slope is 0. To the right of the vertex up to this x-intercept here, our slope is positive. Then our slope equals to 0. And on the far right-hand side, the slope is positive. So now we can start to sketch out our derivative. So let's start with the x-intercept. So at the x-intercept, so when the slope equals to 0, not the x-intercept, when the slope equals to 0, it will be an x-intercept for derivative. So right here, the derivative will be on the x-axis. There'll be another x-intercept for the derivative right there, as well as here. Okay. Now if we go back and start working our way from the left to the right, on the left-hand side here, the slope is positive, which means that the f prime of x is going to look something like this. Okay. To the right of this point right here, so between this point and the minimum here, the slope is negative. Okay, so it's going to be negative, but it's going to come back to that x-intercept. Something like that. That's a little bit crooked, but good enough for this sketch. To the right of the minimum, the slope is positive, and it comes back to the x-intercept right here. So it's going to be something like that. Okay. Then we have an x-intercept, and then the slope is positive. So this is a rough sketch of our derivative f of x. Now let's move on and differentiate f of x, answer in fully factored form. So there is a hint here, and I can't click on it here, but the hint says use the product rule before using the chain rule. And if we look at our function here, we can see it's a product of two functions, so that's where we're going to be using the product rule. But at the same time, each of these functions is a composite function, so you'll have to use the chain rule as well. So we're going to start by using the product rule. So it's going to be the derivative dy dx. And so the product rule states that we're going to first take the first function, just like that. Then we take the derivative of the second function, so it's going to be d dx of x cubed minus x plus 1 to the power of 4 plus the second function times the derivative of that other function, which is 2x plus 1 to the power of 5. Okay, so that's applying the product rule. Okay, let's now differentiate this, being aware that as we differentiate this function here and this function here, we'll have to use the chain rule because these are composite functions. So it's going to be the derivative, hold on, the derivative dy dx of 2x plus 1 to the power of 5. And then to apply the chain rule here, we first take the outside derivative of the outside function, which is going to be times 4. The inside function stays intact. Subtract 1, we're just using the power rule here. And then we're going to take the derivative of the inside function, so dx of x cubed minus x plus 1 plus, and now we're doing the second half here, we're taking the derivative of the outside function, which is going to be 5, inside function stays intact, subtract 1 from the exponent, and then we take the derivative of the inside function, like that. Okay, so let's complete this by finishing up these derivatives. Dy, sorry. So the derivative of the following function is simply going to be, in brackets, 3x squared, that's the power law, minus 1. And then the derivative of the following function is simply going to be 2. Okay. Now, if we look really carefully at this expression, we may see that it consists of the addition of two products. And they also want us to answer in fully factored form. So what we want to see is there a greatest common factor that these two products share? Okay. So we can see that they would share a 2. So actually, let's write down the greatest common factor here. We can factor out a 2. We can also factor out a 2x plus 1. As a matter of fact, we can factor out 4 2x plus 1s. And then we also see that they have the x cubed minus x plus 1 in common. There are 3 of those polynomials here. There are 4 over here. So that means we can factor out x cubed minus x plus 1 to the power 3. So that's going to be our greatest common factor. Okay, so let's factor that out. So if we factor out that as our greatest common factor, then we're going to be left with, so if we take a look at this first product here, we factor out the 2, we're left with a 2. We factor out 4 2x minus 1s, we're going to be left with 1 2x minus or plus? It should be plus, right? Yeah, there's a plus. There was my typo right here. Okay, so if we factor out 4 2x plus 1s, we're left with one of them here. And if we factor out 3 of these trinomials, there are no remaining trinomials of that form. And then we just have the 3x squared minus 1. From the second product here, we have one remaining trinomial. Or actually, let's order it in the same way we order it over here. We factor out the 2, we're just left with a 5, so the numerical coefficient first. And then we have the 2x plus 1. All of those were factored out. And then we just have one of these trinomials left. Okay. Now we can leave it like this in factored form. We could also expand this expression that's in the brackets here, the remaining binomial in here, expand and combine like terms, but I'm going to leave it like this here. So that's C, differentiate f of x. In D, we want to graph our derivative and superimpose it in Desmos to see whether our prediction was correct. So we're looking at this prediction right here. So if we go back to Desmos, and I can now, I've already entered the derivative. If I enable it, that's our derivative. And again, I'm going to take a screenshot just so it's easier to compare. So we're going to go back to our problem right here. And I'm going to paste it in. I'll make it a bit smaller. So if we take a look at the actual derivative here, we can see that we were actually quite accurate. So obviously the magnitude of these minima, which I cut off here and here of the derivative, are different than what we had, but qualitatively we got the slope right. On the left hand side we have a positive slope. Here is our x-intercept, which corresponding to the slope of 0 here. Then we have negative slope. And then over here we have our second x-intercept. We have our positive slope, a third x-intercept, and then finishing off with positive slope over here.